Hey everyone, this is our Lab 9 presentation on magnetic dipole field by Izzy, Kiara, and Chris. The goal of this experiment was to determine the magnetic field strength of the permanent magnet and the distance dependence of the magnetic field due to a small bar magnet. To accomplish this goal, we utilized our phone's magnetic sensor to measure how distance affects the strength of that magnetic field. To see this, we set up our phone with Firefox to assist us in determining the variables that were needed. Here we have the formulas that we use to determine the measures of the magnetic field for both parallel and perpendicular ends, which were used to help us see why we measured in both x and y components in our experiment. As you can see in the first equation, we also derived current and magnetic dipole from the same equation. Here we have a list of the materials that were required to perform this experiment. This includes a ruler, a bar magnet, a phone, tape, a marker, a phone case, a whiteboard which was used as an even surface, and a nail. To begin this experiment, we first had to find the magnetic chip in the phone. To find the chip, we utilized the magnetometer sensor in the Firefox app with the absolute setting selected. We magnetized our nail by putting the bar magnet on the tip of the nail to make it a more precise but weak magnet, and then placed the tip on the phone screen and slowly moved it around until the graph shows when the magnet field strength is at the highest. Once we found the chip, we placed a piece of tape on top of it and marked it. As you can see, we did that here in the video. Measuring the magnetic field of the bar magnet, we also have to account for the Earth's magnetic field, which would make a net magnetic field. To account for the Earth's field, we had to align the phone to the Earth's magnetic north-south axis, with the top of the phone facing north. Just like before, to find north, we rotated the phone slowly until the y component of the graph was at its maximum. This is the position that we used to start computing our data. This picture shows the position of our phone once we found north. Before making our measurements, we determined the base field in both the x and y directions and marked the north pole of our bar magnet because we must have the north side facing south so the magnetic field can go through the sensor in the positive y direction. We proceeded with our measurements with the magnet parallel to the axis of the dipole and measured the x components of the magnetic field at distances 8, 11, 14, 17, 20, and 23 centimeters. We use these same distances for the y component. However, to get a precise read for these, we must turn our magnet perpendicular to the phone so its north pole points south. The reason we are using the x and y components separately is because these components do not face in the same direction. X is parallel to the dipole, while y is perpendicular. In the pictures above, you can see how we oriented these accordingly. To determine the true measurements of the magnetic field for the magnet, we subtract the measured value from the base value, which doesn't include the Earth's magnetic field, which was done through Google Sheets. Here are our results. The x-axis represents the distance between the phone and the magnet, and the y-axis is the strength of the magnetic field of the magnet measured by the phone. This graph shows how different the magnetic strengths of the bar magnet decreased the more we increase the distance from the magnetometer. When measuring the bar, as it is set up parallel to the phone shown by the Bx, the strength of the magnetic field is much stronger than when measuring the bar perpendicular to the phone, By. The Bx average is 0.1065 Teslas, and the By average is 0.1443 Teslas. Here on the left, we had to calculate the amount of current that would have run through the bar magnet if the loop of wire was wrapped around it only once. First, we calculated the area of the magnet to be 1.25 times 10 to the negative fifth. Then, in order to calculate the current, we had to divide the magnetic dipole moment, which we estimated to be 1.254 Tesla, by that area that we just calculated. We calculated the current to be 1.0032 times 10 to the fourth amps. On the right, we then had to calculate first how many times we could wrap this 20 gauge wire around the bar magnet, and how much current would have to run through this solenoid. All we did to calculate how many times we could wrap the wire around the magnet is to take the length of the magnet, which was 1 centimeter, and divide it by the diameter of the magnet, which was 0.81 millimeters, to get the answer of 12 times. To determine the number of atoms in the bar magnet, we had to find the volume of the bar itself. The volume came out to be 1.25 times 10 to the negative 7th. Next, we had to find the volume of the atom, and that was 8 times 10 to the negative 30. Final step of this calculation is dividing the volume of the magnet over the volume of the atom, which resulted in 1.56 times 10 to the 22nd atoms in the bar. We found that 50% of these atoms have valence electrons that have a dipole moment pointing in the same direction of that magnet. That concludes our lab presentation. Thank you so much for watching, and I hope you guys enjoyed. Big Magnet out.